To start recording. Thanks very much indeed. Right, so welcome to Basingstoke's third virtual meeting. Our speaker this evening is Dr. Dirk Frobrecht. He's from the School of Physics at the University of Kent, and Dirk's main research areas are young protostars and their outflows. So Dirk is going to give us a talk this evening about a citizen science project that's running. It's HOYS, the Hunting of Outbursting Young Stars. This is a pro-am project allowing amateurs to update images into the HOYS database, which can also be used by professionals. So without further ado, if I can hand over to Dirk, then he'll give us the presentation. Dirk.
Hi, let me just share my screen, see if that works. Yeah. Okay. So yeah, thank you very much for the introduction. As I said before, this is the first time I'm gonna give a presentation like this. So I hope it will be all right. So the title of the presentation is actually kind of Making Stars and Planets, the HOYS Citizen Science Project. This is something that I started together with Dr. Alexander Scholz, who works in St. Andrews, a couple of years ago. So the official start date, I think, was in the end of 2014. So we're kind of running this now for about 5 years. And during the talk, the main focus will definitely be on giving you a rough idea how stars and planets are forming. A very basic overview, because if I do this properly, this is a couple of lecture courses, so we're not going to do this. But after that introduction, I will try to explain to you why we can actually run this as a citizen science project and how amateur astronomers can help. And I think we're now almost at a stage where the professional telescopes, and I count the one in university as such, don't deliver the majority of the data anymore, and it actually is coming from the amateurs. So we'll be trying to increase that fraction even further. And then I'm going to show you some results, and towards the end, 1 or 2 slides with some basics how to participate. And then, of course, you can ask me any questions that you have. So since about 2 years, we started to publicize this project a little bit more. So I was touring the country when this was still allowed. So this is the 43rd talk in total. As I said, it's the first online one. To get to all the others, I've driven around the UK, about 17,000 kilometers. And I talked to about 1,400 people, 1 cat and 1 dog. So eventually, I hope if someone could make a screenshot, please, when all the Zoom people are back. So I'm going to put this in as a replacement for that. But let's get started with the star formation. So a very, very basic overview how stars and planets are forming. This is best done with a cartoon like that some of you in some form or another might have seen. So stars form in dark clouds, which we call giant molecular clouds. So that would be the first step. These are clouds of gas and dust, so mostly hydrogen, molecular hydrogen in particular, which makes up about 3/4 of the mass of those clouds. The rest of the mass is almost exclusively helium, which is just there, doesn't do anything. And then there's about 1% of the mass is in dust. So these are small solid dust grains, typically silicate or graphite. And they're actually very important, despite the fact that they only make up 1% of the mass, and we come back to them a little bit later. So these clouds, they typically weigh somewhere between a few to a few 10 million times the mass of the sun, so they're extremely massive. And inside those clouds, the material is distributed in different ways. So there will be parts of the cloud which are more dense than others. And it's those dense bits where the stars or whole clusters of stars can form. because the only thing you really need in terms of physics to make a star is gravity, because you need something that collects material in a small central object, and gravity is the only of the forces that can actually do that. So if you have one of those giant molecular clouds, eventually you will get some regions where gravity is the dominant force, i.e. All the other forces which try to disperse the clouds are less strong. And then the cloud will basically start to collapse, which is basically the second item here on that slide. The other dispersive forces, that could be things like temperature. So high temperature gas, the molecules or the atoms, they move quite fast. So that tends to disperse the cloud. If you have rotation, that will try to disperse the cloud. Magnetic fields, turbulent motion, and all sorts of other things that can go on trying to disperse the cloud. But everywhere in those giant microclouds, you will eventually get areas that will collapse, where gravity is basically winning, and very, very quickly the material centrally falls and generates a protostar, what will eventually be the star in the middle. Around that star, very, very quickly, you form what we call an accretion disk. The reason for that is, in terms of physics, what we call the conservation of angular momentum. If you don't know what that means, you might have seen that on TV. If you've ever been bored enough to watch figure skating, you have that person on the ice, they are rotating, they have the arms stretched out, and then they pull the arms onto their body, and suddenly they start rotating much, much faster. And that is basically angular momentum conservation as well. Basically what happens if you have a cloud that is collapsing to the center and that rotates a little bit, and all the clouds will rotate a little bit at the beginning. When the material moves to the center, so closer to the axis of the rotation will basically speed up. And what happens in the equator of that rotational motion is you get a centrifugal force. The same as if you try to drive around the roundabout in your car very fast, you feel that force towards the outside. And eventually, the centrifugal force is actually so big that it stops the collapse. So it balances out against gravity. But that only happens in the equatorial plane. Along the rotational axis, the material can basically keep falling to the center. And this is why you get very, very quickly this flattened structure, which we call an accretion disk. So at the same time, the central object will eject material in those jets and outflows. I'm not going to talk much about those. They typically are there when you accrete material from one of those disks onto a central object. Then material will come out along the rotational axis. We don't yet actually fully understand how they are launched in particular. We know it has something to do with magnetic fields and gravity. But if you ask 10 people how they are launched, you might get 20 different answers. But they're always there as long as material from the disk is falling onto the star. And very quickly after that, the remaining material from the cloud that was surrounding the young star, that gets dispersed because either the outflow material pushes the material away, or the central object, which still is not a star, but it still radiates energy. That radiation will basically also push away the envelope, and the rest of the envelope is, of course, accreted onto the central star. So very quickly, we get a young stellar object, which kind of looks like that. You get what will be the star eventually in the middle. You have that accretion disk where there's still quite a lot of material in it. The material is basically moving from the outside to the inside of the disk and then falls onto the star. That's the actual accretion process. And some fraction, typically about 10% of that accreted material, is ejected into those jets. And it's those disks we are really interested in, because this is where the planets are forming at the same time as the star finishes its formation. So basically inside those disks, material which is made out of these small dust grains initially, these 1 micrometer size dust grains, they will start sticking together and over time form planets like in our own solar system. And eventually, once you get the planets, material can't move anymore across the disk from the outside to the inside, because the planets basically generate gaps, and hence you can't really, so the accretion will stop, and the rest of the material is basically converted into the planets or pushed out. And then you end up with a planetary system when the star basically starts the fusion process, when it is small enough. So the entire process is actually very quick. So if you form something like the sun, that takes 30 million years. But to basically accrete more or less 95%, let's say, of the mass of the final object, that only takes about 1 million or so years. So the actual mass accretion is very, very fast. The planet formation is also very fast. We know that these disks only live about 10 million years on average. That means you have essentially 10 million years time to create from a gas and dust disk with 1 micrometer sized particles, something like Jupiter. That is basically the very basic idea how stars and planets are formed. So now, of course, these clouds are not nice and spherical like in a sketch. So I have a couple of real life data. This is the Cocoon Nebula taken with the Herschel Space Telescope. This is actually one of our targets we're interested in particular the actual Cocoon Nebula, which is on the left. But Herschel images the sky at radio wavelengths, which means everything you see is quite cold. And you also see that these dust clouds, which are nicely visible, they're not round. They're typically filamentary in structure. And in particular, where these filaments meet, you tend to form not just individual stars, but whole clusters. So here, maybe in this point down here, you will get in the future a cluster of stars forming. So all these little white dots that you can see are basically young stars. In any astronomical picture, the colors typically represent temperature. So one thing that you can get from this, if you look at the wavelengths the picture is taken in, and the colors, these clouds are extremely cold. They're only 10 degrees Kelvin cold, i.e. minus 260 degrees centigrade. So they are that cold simply because if they were any warmer, they wouldn't form stars. The material would simply disperse due to the thermal pressure against gravity, and you wouldn't have these filaments and the star formation going on. On the left, the picture is a little bit more blue, and this is where the actual Cocoon Nebula sits. And what happened there is basically about 1 million or so years ago, a whole cluster of stars basically started forming in that part. These stars now, they radiate away energy from the accretion process. So when material falls onto the stars, energy is generated, and part of that is radiated away. And that basically heats the surrounding gas. And this is why that is blue, i.e. It's warmer. So cold colors in astronomical pictures are red colors are cold, blue colors are warm or hot. And this is basically what happened here. So I have a second picture from the Orion star forming region. That's the Orion B molecular cloud, which is a cluster called NGC 2068. That's somewhere here on the left. That's also one of our targets. And again, you see these filaments in the cloud. So they're completely fractal in nature. And the whole complex is illuminated from the right. If you're interested, this here, you might recognize, that's the Horsehead Nebula. So you have a rough idea where this is in the sky. So this direction is north in that picture. And the Horsehead is basically just the end of one of those little filaments. And all the bright stars in Orion illuminate the cloud from this end and heat it up. And that's why that part is blue and the other side is reasonably red. The last example of a cloud I have is actually a very small cloud. It's only about 1 solar mass. It's called B68. And on the left is just a picture that you would roughly see if you had a good enough telescope with your naked eye. So it's optical colors. And what you see is the material in the cloud is not letting any of the starlight through of the objects which are behind it. And the reason is basically scattering mostly and a little bit of absorption, in particular by these 1 micrometer sized dust grains. If you look at longer wavelengths, where you include basically light from the near infrared, so at 2.2 micrometers, and you make a color picture out of that, then you start actually seeing the stars through the cloud. And the reason is there's less scattering at longer wavelengths. It's very similar to the scattering that you get in the Earth's atmosphere, where the blue light is scattered quite a lot and the red light is not scattered a lot, and hence the sky appears blue, except when you look at, right at the sun, and then you see the red light. So basically, the little dust particles inside the dust cloud basically scatter the blue light away. A large fraction of the red light can reach the observer on Earth. What we can do with this is, if you have any idea what the original light was that came from the star, we can analyze what colors do we get on the right-hand side where we observe it. And that tells us a little bit about how big are these dust grains in the cloud, because if they grow, and my typical example is if you make them bigger, let's say up to the size of a brick, then the scattering would not change with wavelengths. These bricks would absorb a certain fraction of the light, but that wouldn't be any more dependent on the color of the light, because the bricks are much larger than the wavelengths. So if you put a lot of bricks up, you will still see a dimming of the light of the star behind it, but the color of the star wouldn't change. Now, of course, typically we can't look around the cloud to actually know the color of the star, so we can't do that. But we'll come back to this later when we look at the accretion disks in young stars. So please keep that in mind for a little bit later in the talk. So what we're actually interested in is basically only two things: is how do the stars gain their mass, simply because the mass is the most important thing of a star. And the second thing we're interested in is how do planets form, but I'm not really interested how things like Jupiter form. I'm more interested in how things like the Earth form, so the terrestrial rocky planets. And they, in particular, they have to form reasonably close to the host star. So within 1 or 2 times the distance of the Earth from the Sun, so a couple of astronomical units. The giant planets, they form further out, but we are interested in terrestrial planet formation. And to understand or find out both of those things, one thing we need to work out is basically, how does the mass get onto the star over time? That's what we call the mass accretion history. And we have to look at the structure of the inner accretion disk. So if you could basically find out exactly how the material in those disks is distributed and what the properties are, then very, very quickly in a computer model, we could run that forward. The computer model is doing this at the moment, but we don't really know observationally how the inner 1 or 2 astronomical units of these disks look like, because they're too small and too far away. So this is basically what we're trying to understand. So this is the only really sciencey graph that I have. This is how we think the mass accretion rate that's plotted here on the y-axis changes over time. So I already told you the whole accretion process takes only 1 million years. This is here. And what we already know is the mass accretion rate is not constant, it changes. It drops typically over time, because eventually the star is finished and you stop accreting material. But that is also not a nice and steady curve. So typically what you get is you get these bursts in accretion, where the accretion gets higher by almost, let's say, a factor of 100 sometimes, for a short amount of time, and then the accretion rate drops back to normal or to a low rate, and then you get another of these bursts. What you don't know is how many bursts do you get and how strong are they? Is there a distribution of strength and so forth? And that is one of the things we're trying to find out. And of course, you can't look at a star for 1 million years. That gets you way past your retirement, so we're not going to be able to do that. But what we are trying to do is basically look at a lot of stars over, let's say, 20 years, look at a couple of thousand stars, and then at least statistically, we can find out in those 1,000 stars over 20 years, that gives us 20,000 years, or something like that, which is a sizable fraction of the mass accretion history. Statistically, how many bursts do you get of what strength? And you might say, okay, these bursts are the factor of 100 higher, but they're very short. What influence do they have? Well, what they do is they increase the energy output by the central star also by a factor of 100. And that puts a lot of heat from the center into the accretion disk, and it will heat it up. It will basically melt any ices that are there, evaporate them. It might even evaporate all the dust grains. So if you don't know how many of these very strong bursts you get, that might actually completely evaporate the inner part of all the accretion disks, then it gets increasingly hard to make things like rocky planets in the inner accretion disks. So we need to find out statistically how this curve really looks like. On the right, on the top here, this is one of those outbursts from F.U. Ori, which is the kind of archetype outbursting young stars that used to be a 16th magnitude star. And then somewhere in the 1930s, within about 3 months, that star got 6 magnitudes brighter, so increased by a factor of 100 in brightness, and basically underwent one of those accretion bursts. And the object is still bright, so we have a rough idea that these outbursts, they last about 100 years. That's our best guess, because we know about 25 or 30 of these objects. None of them has returned to the faint state, so we have a rough idea that they last about 100 years. And you can do some back of the envelope calculations that they should occur roughly every 10,000 years. What it basically means is during 1% of the lifetime of these young stars, the star is in this burst mode, but accretes 100 times more. That means very easily that more than half of the mass of a star is actually accreted in those bursts as well. So they don't just disturb the accretion disks, they also are actually the time when most of the mass in the stars is accreted. So that's why these are important. Now we can have a look at some of those accretion disks. Here are 4 examples taken with the Subaru telescope, which is probably one of the best ground-based telescopes that you have. So the light of the central object is always blocked out, as you can see in the dark spot. And then you can see basically the reflected light on these disks. And you see there's some structure. There's a scale bar, which is quite small, but it gives you typically several hundred astronomical units. So with the best ground-based telescopes, we can see those disks. We can see some structures, like in this one, there's some kind of spiral arm feature coming out, or here there's some weird structures. But in terms of resolving the inner couple of astronomical units that we're after, no chance if you do this with a good ground-based telescope at normal imaging. So how can we do better? So as always, you can throw a lot of money at a problem. You can build the Hubble Space Telescope, costs about $5 billion US, and then $500 million to repair it. And then you can point it at basically the nearest young stars that have disks. They're all in Taurus. They're about 300 light years away. And then you can try to image these disks. And you can see in this case here, this is one of those disks from HH30, where the disk is edge on. So the star is actually hidden behind that dust lane here. So the dust in the disk is basically blocking the light. The disks are not flat. They're not like Saturn's rings. They're flared. That means if you go further away from the central star, they get thicker. So what you see as these white bowls here is basically scattered light that comes from the central star, scattered off the surface of that flared disk, and then back to the observer. And the green thing is basically the jet coming out. There's another of these edge-on disks here where there's no jet coming out, but again, you see the dark midplane where the disk is actually blocking the light. And here as well, the disk is very, very thick, and you have the jet here in some scattered light. But again, you can look at the scale bars, and they're all 200 astronomical units, so roughly the size of the solar system, give or take a bit. And basically, the best detail you can do with Hubble is 35 astronomical units. So again, you can't resolve the inner part on astronomical unit scale, but you get almost a good resolution all the way out to Pluto or something like that. You can spend less money. That's the picture on the right. You use ALMA, which is basically the interferometry array from ESO. That only costs 1 billion euros, so much cheaper than the HST. Works in radio, so what you see is basically the emission from the dust in the disk. And then you can do nice things again in Taurus. Look at the nearest young stars, that's HL Tau, where again the star is in the middle. And there you see a lot more structure. There's rings of material, there's gaps, and some general structure going on. And the resolution for ALMA is much better. So you can resolve structures which are about 5 astronomical units. So the distance from Jupiter to the Sun, you can resolve with ALMA, but not better. And in particular, you can, of course, only do that for stars which are nearby. So in Taurus, most young stars are, of course, further away. What else can you do? You can spend even less money. You build the Very Large Telescope, the VLT in Chile, and an instrument called SPHERE, which basically works in the near infrared with interferometric imaging. And again, you can point this at stuff which is nearby in Lupus and Taurus. This time, these are almost optical pictures, but they look like all the other ones. You get the starlight blocked out, you get these dust lanes, you can see the disks are nicely flared, and you see structure in all of those disks. SPHERE has basically the same resolution as ALMA, so the resolution that you get is about 5 astronomical units. No hope resolving the inner systems here to see how the structure looks like where the terrestrial planets form. And if you're lucky, you find actually young protoplanets in those objects. This is PDS 70, you might have seen that. And this blob is a protoplanet that is forming in the disk of that star. There's a second one hiding in this mess here, but the distance is quite large. So this is probably as far out as Neptune or something like that. If you put our own solar system over that. So basically, with the current technology, we're unable to actually resolve anything smaller than 5 astronomical units in any of those disks. But we will be able to do that. So how does it work? This is an artist impression how the very inner disk will basically look like. You have your central star, you got the disk, and there might be some structures. And let's assume that the part of the disk that is down here is rotating around the star this way, so it's going from left to right. What will happen is eventually this kind of column here of dust, however that is being generated, either because there's a planet here or some magnetic fields, that will move in front of the young star. Now, what that does is it will simply dim the starlight, and it will also make the starlight red. And it will do that for as long as this material needs to, in its orbital path, to cross in front of the star. Once it's on the other side, the star will return to the normal brightness it has. And in this case, a little bit later, you would get a second dip in the brightness that you can also measure. And if you're lucky and this thing survives for one orbit, it should come back. And basically, if you make an educated guess where in the orbit this structure is, then you know the velocity it is moving. That means from the duration of the dimming event and the velocity that you can kind of get, you can work out how big this is. So this is basically the technique that we're trying to resolve structures, is we measure how long the dimming events of these young stars last, and some of them can be very short, and then work out the physical size of these structures. And the best resolution you can get with this is actually down to the size of your light source. So the resolution limit is basically the size of your central star. And all these young stars, they're about 1 or 2 times the size of the sun, which kind of converts to 1 or 2% of the astronomical unit. So this kind of technique, by watching stuff moving in front of the stars and then going out again, that gives you a way of measuring structures in those disks, which are of a size of a few percent of the astronomical unit. That's several hundred times better than what you can do with any of these interferometry or direct imaging techniques. So that's basically what we're trying to do. So, and to kind of illustrate how much better this is, I always use a car, because I was driving around a lot, as an example. So you all know the size of the moon on the sky is about half a degree, and your naked eye has a resolution, so it can resolve things which are 1 arcminute apart. So your eye is actually quite good. Now, what it means in terms of a car, if you have a normal car, your eye can tell if the car is up to 5 kilometers apart, if there's 2 front lights or only 1. If the car's further away, your eye can't tell anymore. So if you compare this to the best ground-based telescopes, where the resolution is about half an arc second, that means with something like Subaru, that 8-meter telescope or 10-meter telescopes, you can see if there's two lights on your car or one for up to 600 kilometers away. So from the south of England, that's basically your car being parked in Edinburgh. With interferometry, things like ALMA or using SPHERE, the VLT, you get to a resolution of 0.025 arc seconds. That's really the best you can do with anything in terms of technology. And that means your car can be basically on the other side of the globe or 12,000 kilometers away. So for the nearest young stars in Taurus, let's say 300 light years away, that corresponds to the distance of Sun to Jupiter, right? That's what I've already mentioned. Now, our technique has a resolution that is 1% of an astronomical unit. But our technique is also independent of the distance. As long as you can see the light from the star, it doesn't matter how far away it is, because what you need to measure the size of the structure is only the duration of the dimming event. Most of the stars that we are actually looking at, they are about 3,000 light years away. If you work these out, that basically means we can see if there's two lights on a car if it is on Mars. That's basically the improvement of the resolution. Of course, we only have one direction. We don't see anything in this direction. We only have the direction it's moving, but that is definitely good enough to get a good picture on the size of any of these structures. One other thing that you get, and that's illustrated on the right, these young stars, they have spots. Similar to the sun, they can have these dark spots. And they can also have hot spots where material basically falls from the center, from the edge of the disk onto the star. All the stars rotate. Young stars typically rotate once a week or once every 2 weeks. And hence, if you get one of those bright spots, if that spot is in the front, the star will appear slightly brighter than when the spot rotates to the back. So you should basically, be able to measure periodic variability from these spots. And ultimately, you can actually find out, if you observe this at several filters at the same time, you can work out the temperature of these spots and how big they are on the surface. If you got good enough data, and I'll show you some later, you can actually see them move. Because if they slowly move over the surface of the star, the face of the light curve will slightly change over time. So you can actually see them move. So these are basically things we can do with exactly the same data by just looking at the brightness of all these stars. We can measure dimming events. We can measure periodic variability. And if you do this in different filters, we can really learn a lot about the temperatures of these spots, their sizes. Remember that the scattering properties of the light also change with wavelengths. So what we can do is, if you observe these dimming events with different filters, we can learn about the size distribution of these dust grains in those disks. We can see, are they as small as in the interstellar medium, or have they started to grow? So kind of the onset of planet formation. So that's basically a rough idea what we're trying to do. And now a couple of words why we think we can run this as a citizen science project with telescopes like this. This is the one at our observatory. So this is admittedly one of the larger ones. So that's a 17-inch telescope that we have at the university. But basically, the project aims to do this photometric monitoring for about 25 years. Because this gets me to retirement. But B, if you're interested in the inner 5 astronomical units, and we want to have structures that come back about 2 or 3 times, so we can actually see that they're really periodic, that would be basically the time frame we need to watch any objects. So that's the 25-year limit. Anything that's further out, we can actually see with direct imaging. So we're not interested in that. You want to do this with high cadence. You want to have 1 or 2 observations per day in every filter. 2 is difficult because from the same location that doesn't work. So that's why we want people in the US taking part as well. Again, that limit is basically if you look at something that is in the orbit where the Earth is, roughly 1 AU from the star, in 1 day, that will basically travel at 30 kilometers a second, roughly the diameter of the sun. So any higher cadence makes no sense because it's still the same material in front of the host star, and we don't need pictures every 15 minutes. So one every night for each object is fine, preferably one every 12 hours. And we want to use all the optical filters, UV-VRI and H-alpha. That's what we do. I know ultraviolet is difficult because telescopes need to be quite large and most people don't have a filter. But that's what we're trying to do for young stars in nearby star-forming regions. So everything we selected is less than 10 million years old because they still have disks. It's nearby, so less than 3,000 light years. That means everything like the sun is still easily to detect with a small telescope. So the sun at this distance would be a 15th magnitude object. That is easy to do. And hence, if we find something interesting, then we can simply use a big telescope to follow this up. That's basically the idea. And in total, we have about 20 or 22 different regions. And we want to use basically these small and intermediate sized telescopes because that's what they can do. And it's an easy project just to take a bunch of pictures. Even 10 minutes of observing time is really enough in a gap in the clouds, something like that. Here are some of the targets. So you can see they're all pretty. The reason they picked them is A, they're star-forming regions, and B, most people will take pictures of them anyway. Things like the Orion Nebula, the Rosette Nebula, the Elephant Trunk Nebula, Pelican Nebula, the Christmas Tree Cluster. That's the Cocoon Nebula I mentioned before. That's how it looks in the optical. All these are very, very nice photogenic objects. So even if you don't want to take new pictures of these things, we are interested in all the old ones. As well as any of the new ones to see what the stars in there have done in the past. So, so why do we need citizen science for that? So on the left is a typical radar picture of the UK, not from the last 3 weeks. The little arrow here, this is where the telescope in Kent is, and you know that typically when you're trying to observe, it's cloudy. And so you have two choices. You can move your telescope around to where it is clear, because I reckon about 90% of the time in the UK, there's always one patch that is actually clear. But it's quite a lot difficult to move your telescope all the time. So we thought, okay, on the right are all the amateur astronomical societies that I could find when I did that list a couple of years ago. And you can see they cover basically the whole country, except where no one lives, and it's very dark, but it's usually raining. But you basically cover with all the amateur telescopes, and there's probably 2 or 3 or 4 good telescopes for each society. You cover the entire UK, so you get a good chance of actually getting pictures of every target every night from somewhere in the UK. You just have to basically get enough people to take part, and that's basically the goal. So as I said, we run this now for a bunch of years. Since 2 years, we're doing really some advertisement. So what we have at the moment is we got 67 different, what I call active participants. So these are people who've signed up and actually delivered some data. They're from 11 different countries. So the pictures basically show you where all the observatories are. So all the blue ones are amateur observatories. Here's a magnification of the UK. We cover most of it, except the southwest. For Europe, we have a huge group in Spain. So Southern Europe is nicely covered. We have the odd person in the rest of Europe. There's a couple of observers now in the States. They can deliver that second data point per day. And we got one lucky German guy who has a remote observatory in the Atacama Desert. So in the winter, I get one picture of Orion every single night because it's clear there all the time. In total, we have now gathered about 25,000 images. Because we know the size of all the telescopes and exposure time, this works out to a total exposure time of almost 600 hours times a square meter for exposure time. So this is basically something like 700 or 800 hours on a 1 meter telescope, pure exposure time. And in total, we've measured now more than 100 million brightnesses of stars in all these pictures, which are now a database which we can analyze. This just shows you how the data comes in. So this is the time. This is correct up till yesterday. And this is the number of pictures that we had. So the blue line basically tells you at each line how many pictures we had. And these are basically the 1st of January every year. So this is the 1st of January this year, last year, and so forth. And you can see since the middle of 2018, you have a really good steady rate of images coming in. There's no dip from the lockdown, so people still keep observing. And our goal is basically to keep this rate coming in or improve slightly to have enough images every night of every target. This is basically the same data, but now it shows the total exposure time times the surface area. And you see the same effect that you basically have a nice and steady supply of data since roughly 2 years now. So here's some example pictures from some of the images. This is basically near the Christmas tree cluster. There's a sequence of 3 images which are blinking. This taken, I think, in 2015. It was one of the first pictures we have. And one of the things you can see immediately, there's a lot of stars that change their brightness, even with the naked eye. So I've highlighted them, all the ones you can find with the naked eye. That is the extreme one that just disappears in one of the pictures. So the images are taken basically 2 weeks apart. So it's basically 1 month every 2 weeks, so 3 pictures. But you can see there's a lot of stars that basically vary their brightness. And most of the stars here are young stars. Of course, we don't do this with the naked eye. We use the computer to measure all the brightnesses. And if you do that, basically every star shows some kind of variability that we can analyze at some level. So much smaller variations than what you can see with the naked eye. As I said, what we're interested in is the images. So once you've done the pictures, you can upload them to our website. I'll show you later how that works. All you really need to tell us is what target field the image is for. And that is basically the only thing you really need to tell us, and what kind of instrumentation you've used. And then we will automatically run astrometry over your images using astrometry.net. You don't need to do that. If you do it, we will wipe it from the image and do it again. But not that we don't trust you, but this is so we have done it really the same way for every single picture. And then we use the source extractor software to do photometry. And do a basic photometric calibration. Basically, you get shown a graph like this, where it plots the brightness of the stars in the picture versus the brightness they should have in a reference catalog. And you're basically asked, do all the red points line up at 0? If they do, then you accept that. And basically, once that is done, then the data is going straight in the database, and it's live for everybody to query and get a light curve out for any object that was in any of your images. One thing we do afterwards is because many of the telescopes have slightly different filters. So there's some people who have a green filter, or some people have DSLR cameras, and so all the filters are slightly different. And what it causes is some scatter in the brightness measurements. And I've picked out a really bad example where once we've done the calibration, you can basically look what is the difference in brightness and magnitude here, that's the y-axis, as a function of the color of the stars in the picture. And you can clearly see that the red stars, they deviate by 20% positively. The blue stars, they deviate by about 20% negatively. So that usually causes a lot of noise in the light curves. But because we have now so many pictures, we know the colors of all the stars, in particular the ones that don't change their brightness. There's enough stars in every picture that are constant. And these are the ones that are actually plotted here. So we know the color and the brightness of all these stars because they haven't changed over 4 years. So what you can do is you can basically try to fit that function here that tells us what is the offset as a function of color. The same here as a function of magnitude. It's actually done at the same time. That's why the fitting line doesn't look nice. And then you simply subtract that fit, and then suddenly all these offsets disappear. So there's no trend anymore with the color of the stars or the brightness of the stars from the value they should have. So in this case, the scatter actually went from 18% uncertainty in the brightness to just 4%. So that's basically what we can do to improve the calibration with the huge amount of data that we have. So that works completely automatically and gives us very, very well calibrated brightnesses. The inference on the light curve is like this. This is a very red star. It has a telephone number here, which I'm not going to read out. And this is basically on the left, the infrared in black, and the red light curve for about 20 days of that star. So you see how much data we actually have, and you see how much it scatters. And that's before we do that correction of the colors. And afterwards, what you can see is the star actually almost doesn't change its brightness, so that the star is almost constant. It varies maybe, if at all, by 1 or 2%. So this is basically what we can do with the data afterwards by simply using all these color corrections. So here you can't actually look for anything like small modulation from sunspots. Here you can easily do that because the noise is so much smaller. Now one nice example of one variable star from a paper that we have recently published. It's called B1496 in the Pelican Nebula. So again, one of those nice photogenic things. This is the star in question. It sits somewhere in the middle of our target field. This is also a graph to illustrate how much data we can gather. So this is the light curve of that star. In green is the visual, or the green light, and red the red light. In black is the infrared light. Over about 2 years before we had a lot of amateurs. So this data is only from our telescope in Kent. And you can count up how many data points you have in those 2 years. It's quite a lot. And then in the summer of 2018, we asked all the amateur participants to simply observe that target field every night, if they could, in all the filters. And here is basically the light curve for that little sequence of about 50 days. These are all the light curve points that we have from all the amateurs. There's more data in those basically 6 weeks compared to the 2 years we had before. And there you can see that the star is actually varying by about a magnitude or 2. And it varies in all the broadband filters in the same way. In H alpha, it doesn't do that. So the H alpha emission doesn't do that. It shows ups and downs. The ultraviolet filter also behaves completely differently. But here what we can try to do is investigate what is causing these dips in the light curve. They look like these occultation events by material in the disk. And the first thing what you can do is you can try to find, is that periodic? So on the top left is what we call a periodogram, which basically just tells you how strong is the signal if you assume a certain period. And what you can see, there's a peak here at about 30 days or about a month. And what you then can do is you can fold the light curve with that. And if this was a nice eclipsing binary, what you would expect is a nice and smooth behavior, which you don't get here. What you see is roughly at phase 0 and 1, the star returns to the bright state, so it's bright. But in between, every time there's a dimming event, which happens every month, the star has a slightly different brightness. So basically what it means is the amount of material that is going in front of the star is different every time it comes around. So I'm going to skip this one. So what you can do is for each of these dimming events, for each period, you can calculate how much material is there in front of the star. So one here is basically 0.03% in those strange units of the mass of the moon. So you don't need a lot of mass to move in front of the star. And you can see it varies. So within one period, within 30 days, sometimes you have almost no material in that place. And then 1 month later, you almost have 0.03% of the lunar mass. And then it can also do the opposite. You have a lot of material and then it drops back down to almost nothing. So we went through quite a couple of months of thinking about what that could be. And the only sensible explanation for this is the following. So we know the periods. We have a rough idea how massive the central object is, which means we know the material that goes in front of the star is 0.15 astronomical units from the star. It's basically the inner part of the accretion disk. And it needs to be warped up and down on the other side. And we are observing that disk almost edge on. We're looking basically just over the edge of the main disk on the outside. And that inner warp every orbital period basically comes into our view and blocks the light. And then after half an orbit, we would basically observe from here, and then we look through that gap, and that's why the star looks bright. So there are not many ways of actually generating that warp on the inner parts. One is magnetic fields, but these warps typically are much closer to the star. So that doesn't really work. So the only other way of doing this is there's some kind of planet in the inner accretion disk, which is also inclined to the main accretion disk. You can usually get that by interactions of planets with each other. And so we think that this is what we see, that this warp that we can basically measure and see that it is at this distance from the host star, that is caused by a reasonably massive planet that is somehow inclined in that inner disk. So that young star most likely has basically an inner massive or not so massive planet. We don't have any idea what the mass of that planet could be, and we don't really know where it is. It can be further out or slightly further in than this distance, but it will be somewhere near the distance. So that's basically what we can do. So these are some other of these folded light curves from the young stars, where you can see basically the periodic modulation. These are all young stars. They vary by typically about a week. So 7 days more typical. And you can see the amplitudes can be quite high. They can be about 10 or 20%. So with the nicely calibrated data, it's very easy to find these things. One thing we've done here, as I mentioned before, we have measured the amplitude for one of those stars over time. And what you can see, the amplitude here starts off for this star at a couple of percent. The colors are the different filters. And then for about a year or so, the amplitude increased and then it decreased, but not to the level it had before. So basically, there are spots on the surface which keep changing their properties, either the temperature or the size of both of them. And this is what we call the phase. This is basically the position of the spot on the surface. And you can again see that changes over time. So that means either the spot is moving around, so by a couple of degrees on the surface, with respect to some fixed coordinate system that goes with the rotation, or you have different spots which are dominating. So there might be a spot here, then a little bit later you might get another spot that appears in a different place. So similar to what you get on the sun. But on the sun, the sunspots also move. So basically, you can trace that over time. Just as a little example. Then, of course, you get weird objects. That's what we call the weird object in the Elephant Trunk Nebula. So 2 years ago, I basically asked a friend of mine, find the weirdest object. Turns out it's this one. It might not sound very weird, but what it does is it has one of those outbursts. But typically, all the stars, they turn blue when they go into outbursts, when they increase their brightness. This one has a much stronger outburst in the red. And it's the only one in about 3,000 stars that does that. So we basically, at the moment, so we asked all the amateurs to follow this up. This is the last outburst, basically the last almost a year now. And we're trying to understand what that object actually is. So that's one of the next papers that we're trying to write. And then, of course, you can, in principle, try to use the data to find exoplanets, or particular young planets. So exoplanets, they change the light by about 1%, you know that. So our data isn't good enough. But if you have a young planet that is accreting material, like the one we've seen, that PDS-70, they have their own little accretion disk, or what we call a Hill sphere around them, that is full of material that is accreting onto the planet. And that thing can be very large. There can be, basically, depending on the mass, cover 1 or 2% of the orbit. And then you could get dimming events, which are quite large, because these things are almost as big as the star, and they could dim the light. So we have one candidate object for that. So the green is our data, the red and the blue are some other surveys, where we think there's an object like that with a period of about half a year, where you have these dimming events, which roughly coincide to integer numbers of the period. So where we have data, they are there except here. There was one occasion where the dimming event didn't occur. if the material basically is moving around the planet. There is some explanation where you could argue why we haven't seen it. The next one is coming up in the next couple of weeks. So starting the end of next week, we'll have to monitor the Pelican Nebula again to see if there's another of these events, and then we're probably trying to publish this. So I naturally haven't put the name or the coordinates of the object on. It's in the Pelican Nebula, so you can make your own guess which one that is. So coming to the end, just a couple of things how you can participate. So we have a website, the address is at the end, I'll leave that on. There's some observing instructions, but basically they say pick any target, which is on the website further down, observe it in any filter, any exposure time, any field of view that you want. All we ask you to do is basically do a flat field and dark correction and stack the images in the same filters over the same night. Then all you need to do is get them onto our server. So you just generate a login, you drag and drop your images, you upload them, and then you do this processing that I talked about. Tell us what is the target. That's basically the only step you need to do. I'm quite happy to do this myself or the other ones, or ask a student if you don't want to spend time on that. And after that is done, the data is basically straight in the database, which you can query online. There's a light curve query. Put your object name or coordinates in, and then you can get any light curve out. There's a download button here that gets you all the data that you ever wanted to get for all the measurements, and you can analyze your own light curve. So the data is public, so be aware if you put your picture in, your data point will be usable by anyone who's querying the database. And then you can get your name on a paper, because we will of course acknowledge that you have delivered data. So the policy is basically everybody gets at least on one paper, and we're trying to write a larger paper every 1 or 2 years with some new technique or a summary of some objects, where we will put all the amateurs on who's delivered data. So these were the first 4 couple of papers. This was the first one about the survey, and starting basically from Roger Pickard, who some of you might know. These are all the amateur astronomers who have contributed data. There's a second page with 2 more papers. That's the one about that star I just explained to you, B1496. And basically everybody after Brinkford-Stecklum is an amateur astronomer. So there might be some people that you know on that list who have contributed to the data. So that's basically what we're doing. We're having 1 or 2 more papers already in preparation. So if you have any questions, the easiest way is email me. We have a website, but the simplest way is to find us on Facebook. And we also have a YouTube channel where we have hopefully this talk on as soon as well. There's already an older talk and all the help videos that explain to you how the database actually works. So that everything is there for you to find out. But any questions, just email me and I'll try to get back to you. Thank you.